Hopefully you found the 14 strings that are generated for n equals 4. We could continue this lab by generating the strings for n equals 5 and beyond, but we won't. It's more interesting to stop and take a quick look at the ways that the Catalan numbers crop up and the things that they count. And spoiler alert, they count a lot of different things. We'll start with simpler ones and then move on to some that are a little more complicated. We already know the binary strings we've been counting contribute to the Catalan series, and it's not too difficult to see how these might be extended to other interpretations. If you wanted to find out all the ways to count 2n votes for two candidates, A and B, in such a way that A never trails B, you can do this by changing the 1s to A's and the 0s to B's. This is often called the ballot problem. If you want to find the different ways to nest parentheses in a string of length 2n, you can do it by changing the 1s to left parenthesis and the 0s to right parenthesis, known as the balanced parenthesis problem. Substituting forward slash and backslash and pushing the string into a second dimension, you end up with a number of ways to make mountain ranges that will never go below sea level, appropriately titled the mountain problem. Getting a little fancier, we can tilt and stretch this result slightly to give all the different paths of length 2 in a grid from 0, 0 to nn that don't cross a diagonal, often referred to as the Dicke path problem in honor of the mathematician Walther von Dicke, who explored group theory with these paths in the 1880s. We'll look at this representation in more detail in a future lesson of this lab. But, as they say on late-night infomercials, that's not all. If you want to do n multiplications between n plus 1 numbers, the Catalan number n represents all the different ways to control the order of multiplication by using parentheses. In fact, this is what Eugène Catalan was using them for in 1838. It is the well-parenthesized product problem. Notice the pattern that involves nesting objects taken two at a time. The Catalan number n can give you the number of binary trees with n plus 1 leaves. This is also called the river problem because it counts all the river systems that occur when you allow at most 2 tributaries to form from each source. If you take an n-sided polygon, the Catalan number is also the number of different ways you can create triangles within the polygon. This is how Leonhard Euler knew of them in 1751, long before they were called Catalan numbers. It is a triangulations of convex polygon problem. If you are interested in how all these representations and more are related, you can check out the link from Professor Ku-Guan Chu, Senior Lecturer in the School of Mathematics and Statistics at the University of Sydney. Mount, ballot, parenthesis, path, polygon, multiply, and binary are all verbs that are available to display their respective Catalan views. In the next section, we'll look at how we might generate the numbers in the Catalan series without even needing to create the objects that we've been counting. For now, play with these representations for a bit, but don't use values much over 10, as the number of objects to view increases quickly, and even with a computer, constructing all these displays takes time and screen space, and each successive number takes more resources than the previous one.